Hello everybody and welcome back. In this video solution, let's dive into the problem diameter of a binary tree. The first thing we'll go and do is read the problem description because there is one line hidden inside of this which is going to make our life simpler. So we're given the root of the binary tree and we have to return the length of the diameter of the tree. A diameter of a binary tree is defined as the length of the longest path between any two nodes. This path may or may not pass through the root. This path may or may not pass through the root. This line looks oddly specific. Okay, let's try to explore this further and maybe there's something hidden inside of it. So on the right hand side, I've drawn a structure where the root node is the yellow node over here and this particular tree has 3 leaf nodes, one over here and 2 over here. In this case, if we try to find the longest path between any two nodes, that is, if we're trying to find the diameter, we'll realize that the answer will come up something like this. In this case, we see that from this particular central point, we have 3 nodes on the left hand side of it and 3 nodes to the right hand side of it. In total, giving us 6 nodes and telling us that the answer for this case is 6. If you try to compute the answer for this guy, you'll realize that you can't go anything more than 5 nodes. Feel free to do that on your own. It should serve as a good exercise. So it looks like this condition is very interesting. And we are sort of finding this path by looking at the number of nodes on the right and left hand sides of it. Let's look at a couple of observations and see if we can figure out some more patterns. The first thing we'll note is that the path always passes through some junction. In this case, it passes through this particular point, which is the junction between the right and left sides of the tree. And so this particular node is a root of this particular subtree. And so it looks like all of these paths have to pass through some particular central junction. And they also have to end at leaf nodes. So in this case, they're ending at this leaf node over here and this over here. And this sort of makes sense. We are trying to maximize the diameter of the binary tree. And so we want to pick 2 leaf nodes that are as far apart as from each other. So since they are the farthest apart, we can get the best possible answer. We can get the longest path. And since we have to connect both of these leaf nodes, we have to go through some intermediary point. Which is why we have the condition over here that the path always passes to some junction. And it may or may not be leaf node. It may or may not be the root node. And that sort of initial condition now makes a lot of sense. Okay, now that we're on this, let's try to find the answer for this particular case. This is a lot smaller and so maybe we can find some pattern here. The first thing we'll do is we want to try and find the answer for this particular node. Let's say that this is the junction we're looking at. Now we'll go ahead and go explore to the left hand side of it and we'll find 2 nodes. Okay, that's good. And on the right hand side of it, we'll find 1 node. So what is the answer for this particular node? Assuming that this is one possible answer, this is one possible junction, what is the answer for this node? It's going to be the sum of all of the nodes on the right and all of the nodes on the left. And in this way, we can do 2 plus 1, giving us the answer of 3. But let's say we want to now find the answer for the root node. Now we have 1 node to the left of it, which is fine. But when it comes to the right hand side, do we need to compute the entire thing again? Well, we know at this particular point, we have to make a decision to either go to the left or to the right. We can't do both. And this is because the structure of binary tree allows us to pick in any one direction. Now, is there something we can use from before? Let's put them side by side. We already computed the answer for this particular junction. We already know the answer for this guy, which is 3. So maybe we can just pass on 3 as the answer? Not so fast. The answer is going to be 3, but because of a different reason. If you look at it from this particular point, we can either select the left or the right paths. Now, which of those paths is the more beneficial one? Remember, the goal is to maximize the diameter of the binary tree. And so it looks like picking this 2 path will get us better answer because it has 2 nodes on this particular side, right? So since we had to decide on one path, let's go ahead and pick this particular path. Now this particular path has 2 nodes on this side, and when we return the answer for this guy, we'll have to return as 3 because we consider 2 nodes over here and this as the third node. And so the final answer for the root is going to be 4. 1 over here and 3 over here. Okay, enough talking. Let's actually go and start coding it. The code is going to be extremely simple and it's a very classic problem. So let's get started. First, we're going to define the DFS of node and we want to do some computation over here. We'll also set up answer, which stores the answer for our solution, and we want to return answer at the end. We're also starting the DFS from the root node. Great. So the first thing we want to check is, well, it's a good idea to look at DFS from the very basics. So we want to look at the base case first. What is the base case? That's when the node is null. That's when the node is none. And in that case, we can return 0. Because from that point, let's look at an example. Let's go back to the very, okay, maybe this one, yeah. So from this particular point, what is the number of nodes below it? It's 0, right? So we can return 0 right away. This is the base case. We have some core logic to do, which is finding out the answer for the left and right cases. Now, how do we find the answer for the left case? Let's do a DFS from the node of left. Similarly, how do we find the answer for the right case? We'll do a DFS from the node of right. What is the answer for this current guy? Let's look at this over here. What is the answer for this node? It's a sum of the right and the left nodes. So we'll do answer equals to left plus right. Now recall that the answer we want is here. So we'll have to do, we'll do maximum of answer comma the current answer. So if this left plus right is the maximum possible value, store that in the answer. Now, what else do we want to do? Recall what we were returning from this particular point to this root node. What did we return? We returned whatever the biggest of these was, for the biggest of left and right was. So we'll say the maximum of left comma right. So we'll find that. And we'll do +1 because this node also has to be considered. So we'll do left plus right +1, left and right +1, and we'll return that. Since this answer is mentioned over here, and we'll just put non-local over here. This is just Python messing with itself, so nothing to worry about. Non-local answer, sorry. Okay, good. It seems to work. Let's try to run our sample test cases. And let's go ahead and finally submit this. Cool. So this works out well for us. And this is it for the solution of the problem diameter of a binary tree. If you like this video, give it a thumbs up. It gives me valuable feedback. And if you want to see more of it, subscribe. As always, thanks for watching.